So let me do this freeform timed assessment demo. As I was saying, I didn't preload the dice this time, so there's a small chance that I'll get the same question, the one question I've done before. If I do, then I'll just reset it and try it again. So here's hoping that the first attempt will get the different question from what I've done before. And we got lucky. So let's do this. Okay, it says in this circuit shown below, they all have resistance R, voltage, capacity. Okay. Initially the capacitor is uncharged. Give your answer to in terms of the given quantities. Let I be denote. Let me start labeling this. This is hard to read and try to keep this stuff in my head. All right. So let's throw stuff so that I don't forget. I have current through the battery, IB. Write down the equation or equations you need to solve for IB as a function of time. You have to use a Kirchhoff's rule. And the reason I look dismayed is, you know what, I can actually make this a little bit simpler. I can treat this entire thing as one junction. Because even though they are drawn separated, they're not actually separated. That's junction 1. And I can treat this entire thing as junction 2. Then this is not quite as complicated of a equation. Because it's a circuit with only 2 junctions. And let's just start writing stuff down. So I got these branches. Let me label this IC, this as IL, and this as IR. Okay, this is making me think. I got 4 unknowns. So let's first write down the first equation. So equation 1, let's use junction 1. The incoming current IB is equal to the sum of all 3 outgoing currents, IC plus IL plus IR. And this is junction number 2. If you're tempted to use it, don't use it. It'll basically give you the same equation, so I have to skip it. So I got 4 unknowns, 1 equation. I need 3 more equations. So those are going to come from my 3 loops. Let me write my loop equations this way. I'm just going to keep things simple. I'm just going to keep reusing this branch over and over. And each of my loops will go like this, and then go like this, and then go like this. Oh, let me, yeah, I think, so let me just, so this is the first loop that I would go. So let me do that. Or let me actually number my equations slightly differently. So I'll number this, my equation, as equation C for capacitor. So for that, my loop rule says I'm starting from here. Voltage rise V0 is equal to voltage drop across capacitor, which is gonna be oops, sorry, not equals. Voltage drop across capacitor. Let me just put it this way: minus Q over C. I think that's the voltage change across capacitor. Yeah. And this sign kind of, it's associated with the relative sign convention for Q and IC. I think this will make, in a normal situation, Q positive minus ICR is equal to 0. And if I'm mistaken, all I get is a sign error that I can flip. So now let me do this loop. Again, the battery. This time the inductor and the resistor, and then around again. So L for inductor is going to be V0. And then let me just do it minus L di dt. And I'm thinking, okay, initially the current will be probably increasing, so di dt will be positive. There's a voltage drop. I think that's right. If there's a sign error later, you know, just invert the signs, this DIL. We'll deal with the sign errors later. And the equation R is now same thing. So, you know, starting from here, loop, this time go through the resistor and then back. Minus I R. R is equal to 0. So those are my 4 equations for 4 unknowns. Yeah. So I'll say we get the following four equations in terms of four unknowns. We eliminate IC, IL, IR to solve for IB. And I'll write down the equations. IB is equal to IC plus IL plus IR. V naught is equal V naught minus Q over C minus IC times R is equal to 0. V naught minus L DI L dt minus IL R is equal to 0. V naught minus IR R is equal to 0. So, good. At time t equals 0, what is IB? So I'm gonna use the hint, and by which I mean let's just erase some of these. It's possible that we don't need any of them. So if I need any of them again, I'll actually sorry, that was a bad thing to do. Let me copy and paste this again because I need to paste in my work at the end. So I don't wanna get rid of what I already do have for A. So let me actually write A here. This is work for my A. And let's do my work for B. That's gonna be. So with the simplifications at t equals 0, so which is, no current flowing anywhere, which means I can eliminate this branch. The inductor is gonna make sure that no current continues to flow through this branch immediately after switch is closed. So inductor branch gone. It's open circuit. Now capacitor is gone, but in a different way. It's gonna go like a closed circuit. Zero charge across, zero voltage, so it looks like just a wire. So I got basically two resistors in parallel. I guess my IB at t equals 0 is simply the voltage V naught divided by the equivalent voltage, which should be half of the R from adding the two identical resistors in parallel. So it should be 2 times V naught divided by R. A very long time after, that is at a time which greater than all those time constants or the oscillation frequency. What is IB? So it's a different kind of thing. Let's redraw the circuit again. So after a very long time, again, the inductors and capacitor go away, but they go away differently for different reasons. Capacitor is now going to be fully charged, and there's a steady state, which means no current through the capacitor. dq dt is 0. So this entire branch is gone. It acts like an open circuit. And inductor is gone, but in a different way. Since a steady current is flowing, there's no change of di dt, so the voltage across the inductor is 0. There's probably some stored energy, but in terms of voltage, no voltage change. So you can treat this like just a piece of wire. So now you have two resistors this way. So our current somehow returns to the same value we are at. So at IB, t goes to infinity is basically the same thing that was there before. I don't know if I would have guessed that without working through this. But yeah, that's the answer you get when the resistances are the same. So how much time do I have? I got 11 minutes. That might be enough time to do but it says without solving the equations in part A. All right, sketch a rough quantitative. That's interesting. Yeah, so I think having done B and C gives me some idea. Because having done B and C, I know some asymptotic behavior of my current. So as a function of time, my IB, I know there will be some value that it's starting at, which is, 2 V naught over R. It'll start at that value, and using this reference line, well, it'll probably come back to that reference line asymptotically over a long time. So the first thing I need to decide is, over time at t equals 0, is it gonna go up or down? I don't know. So I'm looking to see. Let's paste in that thing again. Oops, not that. Paste in this thing again so that I have something to help me think through. So, is there gonna be more current or less current? So this branch remains the same. This branch basically provides a constant value of half of the asymptotic value. So between these two, current through the C branch is decreasing, current through the L branch is increasing. Which is gonna be bigger, increase or the decrease? I'm inclined to say, well, let's see, voltage. So here the di dt is equal to, the entire voltage will be just across the L because no voltage drop here along the register. So di over dt will be V naught over L. And here, well, so I is equal to dq dt, and so double di dt is the double time derivative of that, and will that be q is cv, I think. Am I remembering it right? Let me. Yeah, I think q is a cv. I'm remembering that right. Capacitance times the voltage. So well, the voltage is not V naught. At time equals 0, V is 0. So this double derivative, it's going to be C double derivative of V over dt. And the voltage across that's V naught minus I R. Oh, I see. So there was some so working it out, then di dt is C times the double derivative of that. It's gonna be C times, this is constant, so minus R times the double derivative over t. Unclear. But I think, okay, so I think this is what I have. Di dt here at time equals 0 is some constant value. And di dt through this branch, it's not a constant value. It depends on like a double derivative of current. And if I had to take a bet, this is lesser than this in magnitude. So if I had to bet, I would bet current would go up initially. And then I know it has to come back to this asymptotic value. So I think depending on component values, you could have some sort of like oscillation and then settle on here. Like that's a possibility. That's a possibility I'm willing to consider. Or it could be where it increases for a bit and then comes down. And so I think there are all those different choices. So what I would be willing to put on the answer is, I would say, so we know the value of current starts at 2V naught over R and asymptotically ends at 2V naught over R. So my graph of IB would contain those features. In between, I'm not 100% sure what would happen without actually solving the differential equations above, but I would hazard a guess that the under reasonable conditions, because it's saying this, the current would rise first and then decrease asymptotically to V naught over R value. I also think there may be a small possibility that this would undergo an LRC circuit ringing, which you will see in next week's lab. Um, uh, but attach the figure in the added work is for the possibility above. So I'll answer on this basis, and during the 20 minutes you are really not expected to do more than this. And I think I remember programming in a solution that included the Sage math code. So after submitting, we'll go look at my programmed in solution to see if I did that. But within 20 minutes, I think this is what's reasonably doable. And this is what I've done within 20 minutes or 16 minutes. So let me just submit this, and then I guess I have time to add work. So let's add work, and we'll go in and look at the programmed in solution and see if I coded in a Sage math code. If I did, then great. We can look at the Sage math code to see what the exact answer looks like. If I didn't, then we can curse my laziness and move on. I don't have enough time right now to, even without the time limit, I don't have enough time to do that coding right now. So let me, that's all the work, submit and end. So that's what I've submitted, save work, continue. And within this screen, I don't have access to the answer key right now, but I can bring in the instructor view and use that the way I also did for the multiple choice timed assessment, where I made the same mistake that ChatGPT made and couldn't correct myself well. Freeform circuit, so let me get that. Yeah, test student is the only student who's done it because I just posted this yesterday. So okay, so this is what's submitted, and this I don't have to display again, I'm pretty sure. Let's look at this answer. This is an open-ended question, yeah. Oh, I thought it decreases. Really? Not increase? On one version under, I guess it depends on the assumption. Yeah, so my answer was incomplete. With that, I guess, all right, sure. I'll try with the help of Sage Math, a couple different parameters. So evaluate. So this is one, yeah. This is one where it decreases first and then increases. And I guess I must have programmed in this parameter. And I don't know if I expect the students to get this far. That's in 20 minutes, that's really a lot of, I didn't repeat that bit right now under time constraint. Opposite case where, yeah, then, and then, is it not possible to get a ringing answer? I mean, so in order to get a ringing answer, you do need a small r, I think. Let's see, is it possible to get a ringing answer? So let me take this and just make r really small. Can I do that? Yeah, so I could make r. As I make r smaller, is that gonna mess up? Oh no, as I make r smaller, I think I'm gonna mess up this. So if as I make the r smaller, yeah, maybe. It's possible that I don't get any ringing answer. So I'll try a few. So r at 10% of the original value. Does that. R at, I don't know, 1% of the original value. Yeah, it's possible that you never get ringing answer. Huh. I guess R being in every branch must introduce enough damping that you never get it. Okay, so I was actually, so one thing I am mistaken about it is somehow hoping to get this ringing answer. Let me just do one last try. What if R is really big? like are 10 times what it was, and are 100 times what it was. And yeah, I think including R basically on every branch damps the takes out energy quickly enough that it'll never actually ring. So okay, so I was mistaken about this possibility. And this is an open-ended question. Basically, any kind of thinking that I think this is an open-ended question. Open-ended, many answers are possible. I might need to say, as long as they get the asymptotic behavior correct, that should be considered fully correct. Yeah, so I'll do that edit actually, so that people don't have unrealistic expectation like all these details are some people what people are expected to get in the 20-minute time limit. I do think that's unrealistic. So right, that's it. That's all the time we have.